Anybody have an idea why do helmets or how do helmets protect your head? Claire.
They absorb shock.
They absorb shock.
Cushion. They act as like partially a cushion. I feel like they absorb the impact, so it doesn't like instead of your head hitting and taking all the force.
Yes.
The helmet takes it and like.
So I like what you say, but I want to probe a little bit. So if I'm wearing a helmet and I hit a tree, does my head stop?
No, it pushes into the helmet and
So
then pushes back.
so my head. So if I hit a tree, I hit the helmet, and then my head kind of squishes the padding, but eventually it comes to a stop, right?
Yeah.
So is the force still applied to my head to stop me? Yeah, but so the cushioning is super important, but if you hit something, you're going to stop, so there's still a force, but the force is different. Like if this head hits the ground or a tree or whatever with the helmet on, the tree is still going to eventually push the head backward because it pushes the foam backward and the foam pushes the head backward, and that's what stops the head. But how is that force different from if there were no helmet? It's spread out in two ways. There are two ways this force is spread out. That's a good answer.
Over time?
Over time? That's the momentum and impulse one. It's spread out over time, but it's also spread out over area. So let me get a piece of paper to draw on. Last class I tried to work on the screen and it was just a mess. So this, oh, come on. I just had my camera working and now it's works. Oh no. Okay, there it is. So what I'm getting at is this formula. Ft equals m delta v, and this is impulse. And if this is your head, and this is the helmet, it's a really padded kind of a helmet, and there's your, ooh, you're wearing it over your eyes. Let me put your eye down here. That's going to be your hair. So you hit a tree, and normally when you hit a tree without a helmet on, you get a really big force over a small time, and that's enough to take the mass of your helmet, or sorry, the mass of your head, and change its velocity by quite a bit. But if you have this big helmet on, it's still going to take the mass of your head and change your head's velocity, but you're going to do that with a little force and a big amount of time. So the force is spread over a big time, and it still has the same result in terms of slowing your head down. Here, your head slows down really quickly, and you get a really big force, which isn't so good. And then the other thing is, has anybody ever been on a bed of nails? I haven't either, but I've seen them, and you can lie on a bed of nails, and you're totally okay. This is the person lying on all these nails. No, this looks like a very heavy person, but a very heavy person could lie on nails, and the nails wouldn't poke through. Why? Mass is spread out. So you've got this weight, whatever your weight is, your mass times gravity, and then you've got a force, the force of the nails that's, I'll just call the normal force pushing up, or it could be the nail force in this case. But it's spread out over all these different nails. But if you had a person, same person, and you just put them on one nail, then it would just poke right through the person. So it's a pressure thing. Pressure is force over area, and we haven't really done that. One of the units of pressure is PSI, which is pounds per square inch. So if you look at the helmet, when this head hits the tree, it's not just hitting right here or right here, it's spread out. Even if this helmet was made out of steel, or if it were made out of marble or granite or something that's really hard, it would still protect the head because the head's not being hit all in one place. It's being hit over this broad area. So the force per unit of area is smaller. Uh-huh.
They have like a, it's not actual nails, but it's like the steel's hitting and you press, like you lay on it, you press a button and the steel like rods come up.
And
Same thing.
yeah, so and it doesn't feel like uncomfortable. Yeah. All right. So the homework. Questions about the homework. I feel like last class when I went over this, I did a bad job. I beat the dead horse until the dead horse was pulp and nobody knew what the heck I was talking about anymore. So I'm going to really try hard not to do that this time. But I do want to go over the questions. There I am. 16? Yeah. I feel like 16 and 17 are worth going over, both of them. So I'm not going to read this answer. I feel like that was just, I was getting off on the wrong foot last class. So, and that's what I did. This says, why is momentum conserved for all collisions, regardless of whether they're elastic or not? And the reason this is thrown in is because, you know, some collisions, like the Newton's cradle, when the balls go, that pretty much conserves kinetic energy. But if you have an inelastic collision, it doesn't conserve kinetic energy. But it doesn't matter whether we're talking Newton's cradle or we're talking any other kind of collision, momentum is always conserved. So first I want to write momentum conserved. What that means total momentum stays the same, is constant. And here's why. Could be people in space. I'll make it people in space. We got a couple of people in space. One's a sumo and one is a baby sumo. And they're just floating there in space. And what I'm saying here is for the system of the sumos, within this system, momentum is going to be conserved whether or not, like if I shoot this sumo at that sumo and this one embeds in that one, momentum is going to be conserved. If this one bounces off, keeps all its kinetic energy, momentum still conserved. So it always has to be conserved. Here's why. If, let's say, the big sumo reaches out and pushes against the little sumo with this really long, weird-looking arm, according to Newton's third law, this big sumo is going to apply a force to the little one, represented by that. So if that's true, little sumo pushes big sumo with a force like this, what's the little sumo going to do to the big sumo? Push back with what kind of force?
Same.
Exactly the same force, but in an opposite direction. So if this person pushes that person to the right with this force, then this person is going to be pushed to the left with the same force. So Newton's third law tells us that. For every action force, there's an equal and opposite reaction. Now, this is a rhetorical question. Who gets pushed for longer? Like if this person reaches out and pushes the baby, does the baby get pushed for longer? Or does the big person get pushed for longer? Or do they both get pushed for the same amount of time? Yeah, it's impossible for me to push you longer than you push me. If by me pushing something, it's pushing back, they're happening at the same time. So the forces are the same and the times are the same. So if I just think about what's happening to the big sumo, there's a force applied for a certain amount of time. That's an impulse. And the force is to the left. For the baby, there's a force applied for the same amount of time. The same force, same time, that's an impulse. And impulse, we've already shown that impulse has to equal the change in momentum. So what this means is when one object pushes another, or that's just a shorthand way of saying there's a collision between this object and that object. They're both pushing with the same force. They're both pushing for the same amount of time. The only difference is they're pushing different directions. And a force times a time equals a change in momentum. So what we're going to get here is that the big person changes in momentum equal to this negative force times time. So we're going to get a negative change in momentum, and he or she or whatever is going to start moving to the left. And the little baby is going to have the same force for the same amount of time, and that's going to give a positive momentum, so the baby's going to start moving to the right. These changes in momentum have to be equal and opposite because they're equal to impulse, and the forces are equal and opposite, and the times are the same. So whatever momentum, like positive momentum the baby gains, the big person's going to gain just that much negative momentum. And if you add the same amount of momentum that you subtract, then you get 0. So I feel like I'm kind of beating the dead horse again, but let me summarize. In any collision, could be a sphere and a ball, they hit each other. They both push each other with the same force. They both push each other for the same amount of time, and that means each one causes the same change in momentum to the other. The only difference is one's force is positive and one's force is negative, so one change in momentum is positive and one's negative. And if they're the same and they have opposite signs, then they cancel. So that shows no matter what, no matter whether they stick or they bounce off, because of Newton's third law, you always have to have the same amount of momentum. Okay. I think there are places where I've written that much very succinctly and to the point, but all right. Anybody have any questions about 17? The ball dropped and hitting the plate. When is momentum conserved? When is momentum not conserved? I know you're probably tired of me talking, but how about people at home? Anybody want to know? So yeah. So number 16, I guess I was assuming that in a collision, you know, if these two objects hit each other, we're talking about for this whole system here, because one object pushes the other and the other pushes the one, so their forces cancel out. But if the system was just this object and this one's outside the system, then its momentum would not be conserved. Like the total momentum of this, the total momentum here is conserved. But if you just look at the momentum of the baby, if it's still and suddenly it starts moving to the right, momentum has changed. So, but that would be the case where we're just thinking about the baby and then the big person exerts an outside force from outside the system. But if the system is these two, so this really should say, well, it sort of implies that when it says why is momentum conserved for all collisions, that we're starting with a system of two objects, at least, that are going to collide. If it's colliding with something from outside the system, then it's not. Good. Okay. Other questions? All right. Moving on. 18? Yeah. So the information that you're given, I don't have my questions here, but I could figure it out, I think. There must be a target that's got a mass of 1 kilogram and a projectile that's got a mass of 0.2 kilograms. So this is what they look like together, and then after one embeds in the other, it swings up to some height, and this is the height. So in this first part, I'm saying that the potential energy here at the top of the swing is equal to the total mass, m, times g, times h. So this is the potential energy that the projectile and the target have together when they swing to the top and stop. And here I'm saying that equals the kinetic energy that they had when they were at the bottom of the swing. So moving back a little bit, here the projectile's moving really fast. The target isn't moving. Then the projectile sticks in the target, they start to swing together and they move up. So I find this potential energy, and then I say that's equal to the kinetic energy that it had when it was here. So potential energy is 4.7. The kinetic energy there is also 4.7. And then I find the momentum of these two. But in order to find the momentum here, I need to know the mass and the velocity. So what I'm doing in this step is I'm using the kinetic energy formula and setting that equal to 4.7 joules, which is how much kinetic energy it has. And then I solve for V. So that gives me the velocity of these two things together. I plug in their total mass, which is that, the amount of energy, and then solve for velocity. And then to get the total momentum there, it's just the total mass times that velocity that I just found. And finally, the last step is to say that that total momentum that the box and the projectile shared after the collision was equal to the momentum that the projectile had all by itself before the collision. So here's the net momentum before the collision. The projectile, there's its mass times its velocity. Here's the target, there's its mass, it's not moving. And then after the collision, the two of them have this momentum. So basically, if I take the total momentum and divide it by the mass of the projectile, then I get the velocity of the projectile. Questions? All right. Now this lab that we normally do, I think would have been a mess if I had had everybody try to do it today. So I made this series of videos and explanations that if somebody were not here, they couldn't listen to me. They could just watch all this and figure it out. So if anybody feels like you've just had enough of me talking, I won't be offended at all. You can leave and you can watch the videos and you can do the lab on your own. But I'm going to try to make it a little bit simpler than I made this in the other class and explain what to do. So turn in your packet to page 11. If you have your packet. If you don't have your packet, it's okay. And it looks like this. And I've decided to give you everything except coefficient of restitution. I thought it would be kind of fun to give you the first column of data and the second column of data and have you figure out these, but it didn't look like much fun when I was watching the other class do it. So I'm just going to give you these bits of information. The coefficient of restitution we'll have to figure out. So I don't want to give that to you, or even the formula for how to figure it out. But first, let me explain what I did in this lab. And if you want to watch the videos, you can see me doing it. Last class I tried to show the videos and they didn't work out. So I had this car and I put it on a ramp and I held it up at the top of the ramp. There was this little piece of metal so I could get it all the way up to the top. One end of the car's got a spring that sticks out like this. It's this thing. This is the bad one. Some of them are a little bit better. The other end is just flat. And down here, I had a force meter with a little probe that sticks out like this. And what I would do is I would let go of this thing, and it would roll down, accelerating the whole time, and then it would hit right here, and then it bounced back up, and maybe it started there, but it only bounced back up to this height, and then it would stop. So I would record 3 bits of data: the maximum force, the impulse, and the what did I call it? The separation distance. And let me show you what those 3 things look like. I've got a pretty decent drawing of this. The maximum force and impulse I'd get this way. This is time, this is force, and I hooked everything. I hooked the force probe right there up to the computer, to Logger Pro, and it would record the force, which was 0, 0, 0, 0, and then all of a sudden when the thing got hit, it would go like, it would jerk down and then back up again. And then 0, 0, 0, if it got hit again, it's like this. So one of these shapes, one of these 2 shapes I've got here, is what you get when the flat side with no spring hits the force probe. One of these 2 shapes is what you get when the springy side hits. Guess which one is the springy side? The first one or the second one? The like this, yeah, this is the first one. Would this be the springy side hitting the force probe or the hard side? What do you think? It's the springy side. And this is cushioned, so it's like the warm-up I was talking about. So when this hits, it hits, compresses, and then bounces back. And because this is springy, that lengthens the amount of time. So this is a long, wide band. But if you lengthen the time, what happens to force? It's not very strong. So this is an example of a little force times a long time. But then if you... Oh, must have spun the tires, wheels. When this part hits, then it's hard, so the time interval is really short, but the force is big. So this is like hitting something without a helmet. And so I can get the maximum force with Logger Pro. I can just measure this distance. That gives me the max force. That gives me the max force. So that was one of the 3 things I recorded. The impulse, force times time, is just this area, the area under the curve. And it's too bad you can't do this, but trust me, it'd be a mess if we tried this. And then this is also the impulse, force times time. So that's where I got that. And then separation distance. Here's how I measured it. It was kind of complicated, but mostly I just want to explain to you what it is. Actually, I did closing distance as well. So here's what I mean by closing distance. The distance from this plunger to that force probe. That's the closing distance. And I call it that because in a collision, when we're trying to calculate coefficient of restitution, we do separation speed over closing speed. So this is analogous. This is the closing distance as it's coming in to hit. And then when it bounces back, the separation distance would be this. So this is how far it travels on its way in, and this is how far it travels on its way out. So if it basically falls this far and then bounces up that high, is this 100% efficient? Does it keep all its energy? No. Coefficient of restitution is going to be less than 1. It's not really efficient, and every time it bounces, it's going to be much less high than it was before, and pretty soon it's not going to bounce back up. So those are the bits of data that I've given you. And let me go to Google Classroom and I'll just show you what this looks like so you can see where it is. It's kind of slow. All right. So there are two data sets. There's one where you have to actually figure quite a bit out, called collision data for student use, but I would go ahead and skip that and use collision data with linear separation distance. So here we go. And again, probably better to have collected all this, but I did it for you. So the first kind of collision, I did this a bunch of times, but I only recorded three collisions. So this is when the flat end of the cart hits the probe. These are the maximum forces in the 45 range. If you look down at the spring end, it's around 14 or 15. So you can see how those are different. The impulse, that's the area under the curve. So that was this area. There's an integral tool that I can use in Logger Pro that gives me that. So this is the force times time. And you can see they're not too different. This force is about 3 times as much as that force, but this impulse, just a little bit more than that impulse. Linear closing distance is the same. This is the distance that the cart accelerates down the track before it hits the probe. And then the separation distances, these are how high the cart bounces afterward. So what you have to fill out on your sheet is the coefficient of restitution. And to do that, you're going to need to do some math. And to do the math, you're going to need some kinematics formulas. So what I want to do right now is give you this whole problem. All the people at home, I encourage the other people to work together, but I think people have forgotten how to work together. I'm going to mute my, going to change my speakers so it's going through my laptop, and then I'm going to mute my laptop. So if all of you want to talk to one another, you can do that. And I'm going to want you to try to solve this problem while the people in here try to solve the problem, and we'll see how people do at this. Here's the problem. Suppose you have a ball and it falls a height of 60 centimeters. And then it bounces back up and it only reaches a height of 40 centimeters. What is the coefficient of restitution? So I'll remind you that the coefficient of restitution is the separation speed over closing speed. But you're not really given speeds, you're given heights. This is kind of what's happening with the cart, although it's not falling straight down, it's going down a track. But if you can answer this, you can do the cart thing. And now I'll give you the kinematics formulas, because a lot of you have forgotten them. There's only one of these that I would really need to do this. Average velocity is displacement over time. Average velocity is initial velocity plus final velocity over 2. Acceleration is change in velocity over time. Final velocity is initial velocity plus AT. And then the two displacement formulas. V0t plus 1/2 AT squared, and V squared equals V0 squared plus 2A delta X. So get together, see if you can find that. If you're at home and you think you've got the answer to the problem, put it in the chat and I'll see if anybody has a right answer. What is coefficient of restitution? So you all work on it. You can talk to one another. You can put all your brains together. If I have to, I'll show you how to do it. But you can't go on with this lab until you know how to calculate the coefficient of restitution. Ooh, I don't know. You might be able to use potential energy in this. I would say probably, I don't know, not as relevant as it would be if, so the coefficient of restitution we know is not 1. So energy is not conserved here, which makes the potential energy formula a little less useful. You don't have time. That's a hint. I mean, you might be able to find time. What's that?
It rules out like half the time.
Wait, is all you have distance?
All you have is distance.
How is that?
And this is similar, you know, where we're going with this is when this cart rolls down here, we've got this closing distance and then we'll have the separation distance, and it's very much like that. So if the cart went from 60 centimeters up here and then bounced back up 40 centimeters, we could get the coefficient of restitution the same way for this that we can get it from this. Two people got it simultaneously in the other class. Nobody's worked together. Somehow it just hasn't seemed to caught on, this idea of working together today. So if anybody at home thinks they have an answer or a possible answer, just put it in the chat and I'll tell you if you're right. I still got you muted so you can talk if you want, but it doesn't look like you're talking to one another. Your cameras are off. Maybe I should unmute because nobody's saying anything anyway.
Is the acceleration like just grounding?
Yeah, it would be. Here.
Wait, so is it from the top to like when it's on the ground? Or
So the collision is happening right here. There's a collision between the ball and the ground, or the ball and the earth. And we're looking for the coefficient of restitution of the collision. And the way to do that is to divide the speed with which they separate as the ball's going away from the earth by the speed with which they come together as the ball's falling to the earth. So basically it's this speed divided by that speed. Oh, somebody's got an answer. Iris. Yes, Iris got it. So you got it right. I'm going to give people in here a little longer to think about it. Can anybody suggest a formula? Which one do you think is the most useful here?
Using the v squared.
Yes.
0,
Yeah, why is this one good?
because you can use the height.
Right, so this doesn't have to be delta x. This could be the y displacement. So I could write this as v squared equals v0 squared plus 2a delta y. Do we know the acceleration? Yeah, so it'd be negative 9.8. And we would know either this or this depending on what we're trying to do. I'm going to hold on a little longer. It looks like there's some people in here with calculators out. And oh, now the people at home, if you can, or Iris, if you can figure out a more general way to do it. So let me call this the closing distance and this is the separation distance. So there's no number in here. I just want a formula given this closing distance and separation distance. What would the formula be for the coefficient of restitution? Because we're going to need a general formula we can keep applying. Is anybody close enough that I should wait?
Yeah, I just wanted to say.
Get an answer?
Yeah.
What'd you get?
19.8.
No? You got that too?
But I did it wrong. Do you have to do the equation?
What's that?
Do the equation?
Yeah, because you're going to need this speed and that speed. You have to find the ratio. David?
I'm
You-
getting there.
you
I
getting
found
there?
the separation speed. I'm trying to find the closing speed.
I'm going to write a little bit down just to set the stage for my explanation when I get there.
Alright, I got an answer.
What'd you get?
Negative 0.158.
No?
Ah,
But see if you can figure out what happened. I bet you something simple probably went up, happened along the lines. So here's
or actually, the answer would be positive. It would be 0.158.
0.158.
Yeah.
So I'm just labeling my givens right now. I'm going to be doing two problems basically. I want to find this. I want to find the closing velocity, which is the velocity right before this hits the ground, and then I want to find the separation velocity, and then I'll convert those to speeds, which just means make them both positive. So my first problem is to think about this falling. It's going to be falling from an initial velocity of 0 up to its closing velocity. The acceleration, I can say it's negative 9.8 meters per second squared. It doesn't really matter what it is. As long as the acceleration on the way up is the same, I could just leave this as A in my calculations. And I think I might do that. And then this is my delta y. And then when I do this again, this is going to be my delta y. So for the falling part, if I'm using this formula, my final velocity would be the closing velocity. So closing velocity squared equals the initial velocity squared. Initial velocity is 0 plus 2a. I'm just going to call this a because I don't really need to put it in. You'll see. Delta y, and y is negative 60 centimeters. And I could just call this delta y. Actually, tempted to leave it that way. Just going to call it delta, no, 60 centimeters. But it's negative 60 centimeters. So if I'm solving for the closing velocity, it's going to be the square root of all this. 2 times a times negative 60 centimeters. And it's okay that I've got the square root of something that looks like it's negative because the acceleration is actually negative because it's downward. So this is going to be positive, and I'm going to get a positive number in the end. Or I'll be able to take the square root of it. So that's the closing velocity. And then for this part, the final velocity is going to be when it gets to the top. So the final velocity is 0 squared. And then the initial velocity is this separation velocity. and 2, again, I'm just going to call it 2a, and then delta y is 40 centimeters. So to solve this, I'll subtract this from both sides and then take the square root. So it's going to come out as Vs equals the square root of negative 2a times 40 centimeters. But again, the fact that it looks like negative under the radical, it's no problem because the acceleration is negative, so these cancel out. So basically it's the separation speed is the square root of 2a times 40 centimeters. So if I calculate the coefficient of restitution, it's going to be the separation speed, square root of 2a times 40 centimeters over the square root of 2a times 60 centimeters, which is equal, this part, I could factor out a 2a from the top and the bottom, and those are just going to be 1. So basically this is the square root of 40 centimeters over 60 centimeters. Or more generally, this is the square root of the separation distance over the closing distance. And that'll work on this cart. In this particular case, it's 4/6. So the square root of 2/3 is about 0.816.
I thought you were trying to find the separation speed.
Yes.
Oh, so you're not.
Yeah. The separation speed is this. That is the separation speed. The separation speed is 2 times the acceleration of gravity times the separation distance. And the closing speed is 2 times the acceleration of gravity times the separation distance. So this is the separation speed, this is the closing speed. But it turns out that, so there are a couple of different formulas for E. You can do separation speed over closing speed, or the square root of the separation distance over closing distance. At least in this bouncing kind of thing. All right. So now you know everything you need to know to do this. I'll just point you back to here are all the data. I kind of feel like now I should have just given you a sheet with all this on it, but you have to transfer these data to this sheet, and then once you've transferred those data to this sheet, you have to calculate, well, get an average coefficient of restitution. I don't think you really need to do it for each of these three. You could probably just do it with this average value and this value. And then once you've done that, there's some questions on the back. I don't want to flip this over because you can see them. Try those questions, and the questions are really the main focus of this activity. And they're going to be due on Wednesday. So tomorrow we have the test retake for anybody who wants to do it. There's going to be another homework assignment. Just try to get these calculations done and the questions on the back done by Wednesday. Also on my website and in Google Classroom, I've got a little so-called discussion. So if you click on this, the video discussion, I explain everything. I go over all my answers and talk about it. So feel free to look at that.